we should start. Good morning. This is week 13, lecture 8. So week 13, lecture 8. Okay. Today we are going to wrap up regarding actual infinity loop shaping. And then we'll move to gap metric. I give you this basic idea about what is gap metric by showing you some of the amazing facts. Okay, amazing facts. So remember. Okay, we're doing robust control. Okay, we're doing robust control. Meaning, I'm going to design a controller K to control a family of plants, okay? Or a set of plants, or infinite number of plants, okay? Infinite number of plants. Okay. It is very natural to ask for plant 1 and 2, okay, in a family, how we can say which is harder to control. We ask this question, okay, which is harder to control, okay, or this P1 and P2, and what's the distance between them? Distance between plants. Okay? Okay, you have any two of them into the family, and what's the distance between them? So these are all the questions that we need to think about. Okay, we need to think about. So here's a mini plan. This is November 18th.
18.
That is Monday. And next Monday will be 25. Okay. So then Wednesday is 20th, right? So then it's 27. So we are going to have all the lectures. Okay, all the lectures. Do you know what is the last day of the lecture? Last week? You don't know yet? Can you check for me?
Yeah.
So, but I have a hard constraint. I'm going to leave 13 for a conference. So we need to finish all the FISP before that. Okay, before this 13, maybe 12. Okay, can you check me what is the
Fall instruction ends Friday, December 13th.
So that is our last. What is this is a Wednesday or Friday?
Friday.
This is a Friday. Okay, it's Friday. So our instruction will finish by here.
Mm-hmm.
So ideally, so I have a meeting until I return back to 20th. Okay, return back to 20th. So I'm going to do presentation. Okay, presentation on like 12, 11. So that is our presentation day. Okay, our presentation day. Okay. So by this time, probably this time is our report. Everything due. Report. Everything due. Okay.
Mm-hmm.
Then when I come back, I'll make an assessment and give you guys a grade. So between that, we have, so this is 13, this is 14, and this is 15. Monday is, can you check?
Monday
Is 12, it's no,
Monday is 2, December 2.
okay. Wednesday,
And December 4.
okay. So Monday,
9 and 11.
So we are not going to do any lecture in this week, so week 16. So I will, no class. So I will let you have time to prepare for the presentation and read. So it's called Focused Independent Study and Presentation Week, okay? So this day we are going to do 20 minutes per person, 25 minutes per person to do a presentation using our class time. We'll not going to have class in here, we'll see, okay? No class. So we have 1, 2, 3, 4, 5, 6 lectures left, okay? And we are going very fast. So even like today, we are going to do gap metric, okay? Gap metric. What are the topics we can do in the next 5 days? Okay, 5 days. We can do quite a lot. We can do quite a lot. So one of the things, like I said in the syllabus, check the syllabus. I said I want to do classical optimal control, okay? And contracting maximum principle based, okay? So optimal control problems, okay? That's important for a lot of people. They don't know how to do optimal control. So therefore, I'm going to do this one probably first and introduce you to this software package. You can solve your problem. I believe every student in my class should learn this one and learn the theory behind it, okay? So that probably will need some time to cover this. Another one is fraction order control basics, and also trying to talk about the discretization issue. Okay, talk about discretization, how to implement it, and model fitting, modeling, fitting, and we are going to talk about loop shaping using fractional order control. Okay, loop shaping is fractional order. So I'm going to introduce you a few things. I would like to say this is like bodies. Bodies ideal transfer function. I can say this is a body's ideal cutoff. So I'm very familiar with all these topics. I hope I'll give you some ideas in here, okay? And say, for example, flat face design ideal. Flat face ideal. Okay. I'll explain this one. So I can show you that fractional calculus-based control can help us to do better job in loop shaping. So those are the basics. And yet, finally, I hope, I'm going to talk about MPC, okay? MPC, model predictive control. Because inherently, model predictive control can achieve optimality. And for those robustness issue, they can handle this one by what? Constraints, okay? Formulated as constraints. Okay. So that's our roadmap, okay? That's our roadmap. Again, we don't have a class in here. Okay, we don't have a class in here. We have a class in here. Okay, I'll send a notification to you.
Dr. Chen, according to the calendar, said that 27 is non-instruction.
Okay, we lose one day here. It's okay. This is our third time we lose our lecture. Okay, this is Thanksgiving Day, right?
Mm-hmm.
Thanksgiving Day. Yes. So we're going to lose something here. But anyway, I'm also hoping you understand that robust and optimal. Okay, are two very important features in anything. Okay, in anything, not just control. Okay, not just control. Okay, say for example, deep learning. For example, Professor Lu will mention about optimization today. Okay, so we can always ask, what is the robustness, and what is the optimal way to optimize? Is this optimization process optimal? Can we have a better optimization process? So on and so forth. There's so many choices there, and there are also so many different descriptions of the uncertainties. So that as a big domain. So uncertainty, we say modeling. Okay, people say, I usually say characterization. Okay, but in many other fields they say quantification. Okay, so we focus on uncertainty modeling part, where the uncertainty could be static, could be dynamic. In other words, our delta is not only just a number, but it can be a transfer function. It's like this. And this can be from a structured family, okay? Structured family. Okay, so this is structured family of family, okay? So all this, I hope we want to see in the end what we expect from this class. Okay? I hope this is okay. So let's revisit our syllabus, okay? Syllabus. From here, I said we are going to talk about H infinity mu synthesis. So interval polynomial approaches. Okay? That part probably we are not going to cover. You can use it as your FISP topic. But on the other hand, the interval polynomial approach, you can use LMI to do that. So we're going to ask Sina to cover self-optimizing control. I'll cover fraction order control ideas. Network control system, actually you can we can ask Hyro to present. Okay, focus on that. Finally, horizon control is similar to model predictive control. You have a horizon, okay? Your horizon. So, according to our topics here, today we are here. Okay, today we are here. Okay, gap metric. So for that, we need to review H infinity optimal control, as well as H infinity loop shaping, okay? So you can see H infinity loop optimal control solution is an iterative process. And I highlight that in Cummins' book, they all focus on unstructured perturbations. Therefore, for structured perturbations, there is another separate framework. Okay. So let me go through here and try to see whether you can remember this. Okay. This one shows BPK, okay, shows BPK, and the definition of B optimal, okay, B optimal. So this is actually what they call Gannon 4, Gannon 4, okay, Gannon 4. Let me write here so you can take a look. Gannon 4. Okay, so assuming this is a cycle case, so I'm going to like 1K, and I have 1 plus PK. The PK means plant, and the controller K is sometimes I write L, is my loop transfer function, right? So I do this one is 2 by 1 and 1 by 2, then we'll add up with 1 P. So this will be 2 by 2, okay? 2 by 2. So the 2 by 2 will be 1, and you have P, you have K, you have KP. Okay? Just imagine that you push in this thing here, so you have 1 plus PK, you have 1 plus PK, you have 1 plus PK, you have 1 plus PK. So then I'm going to ask, what's this, equals what's this, and what's this? Okay? Okay? So then you will understand. So this is called Gannon 4. Gannon 4. But to what kind of notation here? Okay, so here is what we are going to do. So this is K, this is P, this is Y, and you have this is E, this is a reference. Okay? Reference. So then you will have a negative feedback in here, okay, feedback in here. So I hope you can understand, okay? Y equals reference. So this is reference, okay? This is my reference. R, this is my Y. Y is this guy times this guy, and times this guy times that. So we should have 2 inputs. What are the 2 inputs? Okay? So what's that? So this is my control signal, right? U, okay? Control signal U. So Y equals R times this one. This is closed loop transfer function, right? Y, R, and the closed loop transfer function, KP. So then we need another one, which is noise in here. Actually, we should put noise in here, okay? Noise, okay? So this should be noise, okay? Should be noise. Okay, but what is this variable? What's the variable? So this one, so we have noise, okay? Noise. The noise adding here is the same thing like adding here, okay? The same thing. We move to here, okay? Let's do derivation, okay? So n plus y, n plus e times kp is this one. This is e times kp plus n, okay? That equals to y, okay? Equals to y, okay? Equals to y. While what e equals r minus y, okay? Minus y. So I'm going to replace the e here, okay? Replace the e. Do you see it? Okay? So I'm going to replace it. So I'm going to have y equals n plus r minus y, kp, okay? So then r is my input, n is my input. I want to get y out of it. So it's 1 plus kp y is n plus r times kp. So if I do this one, I'm going to have y equals n, let's do this, 1 over 1 plus kp times n plus kp 1 plus kp times r, okay?
Then here we have an extra k then. And the first term that is multiplied by n. We need a K here.
Then that means we put this n into, do we have a K? No, we don't. So that means our D is here, okay? Let me see. If I put the n in here, so let's do the D, don't do the n, P, do the P. Then you have a P, right? So let me do this one. So this is okay. If n is here, I have this result. If d is here, then I'm going to do d plus k times e, okay, and times p, d, ke, and times p will be my y, okay? Y. And e is r minus y. So now it's going to have a k, okay? So then here should be d, okay, later. So what I'm going to do here is d is my input, k r minus y is the kp, and d you have p, okay? You have p. Then you have y here, okay? So then you are going to have a pk, 1 plus pk, okay, times r, and you have a p, 1 plus pk, times d, okay? So we solve probably this problem, okay? Okay. So we probably have p is in here. Okay, this is d. Pk is r. Then this is also y, okay? So we need to define another output. I think another output is, one is from here.
But then it's still here, y.
So they have 3 inputs here. This is n, this is d, okay? Then you can pull out, so this is my output. I can pull out this signal as my output, can I? I can also pull out this signal as my output. So this is my controller, this is my controller, right? So it's always possible. So then we pick up 2, so we can write this way, right away. So, and you can see this is actually, this is complementary sensitivity function. This is complementary sensitivity. This is sensitivity function. Okay, sensitivity function. And I think this is this is related to control signal. This is related to disturbances. Okay, disturbances. Okay. So, but anyway, it's possible to interpret in such a method. Usually, previously, people write in 3 by 3, it's a GAN of 9, okay? GAN of 9. But the easiest one is called GAN of 4. So you can see here you have this is E, this is U, okay? This is U. So you have a N, D, R as input, this one as output, okay? As output. So this is to understand the sensitivity, okay? Understand the sensitivity. But in here, you can see we only focus on GAN of 4, this format. GAN of 4. So we try to make this matrix and put into an infinite norm. Then you do the inversion. So it's kind of metric. If K can stabilize that P, okay, we call it BPK. And then we search for a K such that we have B optimal, okay, B optimal. And this B optimal, okay, this B optimal is very interesting, okay, very interesting. And I want to show you. So the question is B optimal? here, can you read here? The B optimal, searching along K, it turns out that, listen carefully, okay, it turns out that this number has nothing to do with K, okay? It's already only linked to P. That means P, you write a normalized left co-prime factorization and check its norm, and this one has been proven is already B optimal. So in other words, can we tell a piece of wood is a rotting wood? Is this system hard to control before you even design a control? You can tell, isn't it? Isn't it? Okay. So that's kind of interesting. So this is already, you can tell without knowing your K. Without knowing your K, it is only linked to the original plant P. Okay, plant P. And actually, in a state space realization is connected to state two algebraic Riccati equation solutions, Y and Q. So you can refer back to what's that in H infinity control formulation. And for single input, single output, people can already show that the system gain margin for whatever K put there, it has a lower bound, okay? It has a lower bound by this number, okay? And the phase margin is also given by this one, okay? So in other words, this BPK, okay? Peak value is this. Peak value is maximum, okay? And in other words, if you choose non-optimal K, then this one will be smaller, okay? Will be smaller. If this is smaller, okay, the gain margin is also smaller, okay? So that gives your best margin already, okay? Best margin already. So phase margin is bottom, is linked by this way. There was a proof about this, okay? So this is a closed loop transfer function. So then this is a closed loop gain, closed loop gain, okay? Closed loop gain, okay? And this is true for all omega, okay? For all omega. So then you try to simplify notation by writing the loop gain, okay? Loop gain. But it's a complex number, no loop gain here. Minus pk here, then this is 1 minus k is the same as this. Others is just a mod. By simplification, you can get this k square, and this one end up with this format, okay? This format. When you try to search for the minimum points, so you get an upper bound. So that implied all the gains k, this is the gain, okay? All the gains k is bounded by this. Or you change the sign, okay? You change the sign, you have this, okay? So this giving p and giving k, here we are talking about MIMO case. You can always get a BPK like that. So you can imagine, what is the BPK? BPK is an indicator that, so what is the peak, what is the actually infinity norm of this person, okay? Of this 2 by 2 block matrix. In the MIMO case, it's difficult to do, but in MATLAB, they already prepared a command for you. And giving a plant, you can always choose what is your k optimal. Then you can choose suboptimal by putting argument 2 in here. Okay. So for k optimal, there is a corresponding BPK that serves as a bound. Okay. So these malloc are useful for you to do some research on that. So, in fact, what is the guideline to do? What's the guideline to do loop shaping? We have learned that in the lower frequency part, the gain should be high. High frequency part, the gain should be low. Okay, should be low. That kind of loop shape is what we want to achieve. But in math language, is to say that before you do the loop shaping, you have a system coperimeter factorization normalized, okay? And this is the minimum singular value of this matrix, okay? So we denote this is lambda p, okay? So this lambda p is set up the upper bound of the B optimal. Remember, B optimal is for all controller k searched for the maximum one. And this maximum one has to be less than this, meaning this is already verifying the saying as I gave you a long time ago. If this is too big, so this is a rotten wood, you cannot really do a very good job about it. Like you did the inverted pendulum on a cart. It's a piece of rotten wood. It's hard to carve a nice performance out of it. So it's very sensitive. So this one says the same, okay? It says the same. Okay. So then they are trying to talk about right half plane 0 and right half plane pose. So right half plane 0 is also called non-minimum phase 0, NMP, non-minimum phase 0. So for project 1, I hope you already had some appreciation about how hard the system is when you have right half pole as well as the right half zeros. So these Z's are just right half plane 0. So basically, you have some format like this. Okay. So they want to do extract all of these, extract all of NZ and NP like that. Okay, so these are the right half plane. So what they do is funny. So they just put the Z1 plus zeros. If you have a 0, I add this one. If you have a pole, then I add this one. Okay, add this one. So then you have a P0 will have no open right half plane poles or zeros. Okay. So in this case, the optimal B optimal is decided by both. Okay, this one N0, M0, NP, and NZ. Okay. So this one is very similar to the body's gain phase relationship. Okay, gain phase relationship in a MIMO setting. So I'm going to get this one over. So when pose zeros are very close, you are very hard to control. So here there's an example. There's an example. So you put a K in here, and you have R in here. So you have R change is almost 1.1, close to 1, 0.9, close to 1. So depending on the K, the B optimal, okay, with this P1 is different value. So different value. So very small for all K whenever R is close to 1. So if R close to 1, this B optimal is like always 0.00 something. one order of magnitude smaller. Okay? So that means what? That means when you have a pole and zero close, unstable, close, then it is very difficult to control no matter you put what kind of controller K in here. All K's. Okay. So here you put a different K, you change the value here. Okay, change the value here. But here you can see when you K increase from 2 orders of magnitude, and these values are still small. So that inherently tell the system is very difficult to control. Okay? To control. So we are going to skip this part. Okay? Skip this part. We are going to talk about gap metric. So let's start by looking at this example. Okay, this example. Okay. So I'm asking a question. There are 3 different plans. One is this one, open loop stable. Another one, this one is open loop unstable. And this one is a different relative degree. Okay, open loop stable. Okay. So I want to ask you that having a controller to control this, okay, which one is easier? And if we measure a distance between P1, P2 somehow using some metric, okay, and P2, P3, P1, P3, okay. So we want to say that so if you already design a controller, okay, for P1, will do well for P2, but not necessarily for P3. So in other words, these 2 are closer, and this one is not close. So there's a simulation example here. Okay, so simply using a step feed, using a proportional control with K1 is 1, you can see the first 2 P1, P2 are P1, P2, but P3 is unstable. P3 is unstable. So that means we need a way to tell, okay, how we can measure the distance between different plants. Okay, different plants. This is important. Why? Because robust control is to deal with a family of different plants. Okay, different plants. Okay, so we really need to understand what's the membership relationship. Okay, like you are inside a family, then what is the distance between that? Say I ask you a question, very simple question. I have this big set of plants. Where is the center of mass? Where is the center of mass? Okay, is a value. So then we say this center of mass is considered as equal distance to anybody. Okay, can we find that point? How? You need to define the distance, right? And with meaningful method. This was asked but not well answered until a person called Winnicott. He published a series of papers. He wrote a book also on gap metric. Okay, gap metric. So we need to understand. So what is the gap between here and here? So we are in the same family, but the different members will have different distance between them. How we can measure that in a meaningful way? That's the question we need to answer for this chapter. Okay? So this is chapter 17 regarding gap metric and mu gap metric. Okay? Remember, we do optimization is based on certain criteria or performance metric. So if you have a new metric, this is new metric, we do have a new metric. You have a new metric relative to the old metric, then you will have a new framework of doing optimal control. Okay? And H2, H infinity, just two popular metrics, understand? We remember we still have SSV as a metric, or structured singular value as a metric. Now, in that sense, we are introducing you another metric. And using this metric can guide us to do what we call extended loop shaping design. Because our loop shaping previously is based on H infinity, okay? H infinity. Yes. After the loop shaping design, we may have a very high order controller. We did the controller reduction. We did it in a separate chapter. I think it's 15, right? So, okay. Okay, shall we start about the gap metric? You have enough motivation to talk about it. So let's go to a very simple example here. So you have a plan 1, you have plan 2. You consider this one is perturbed by, based on this, you can say whatever way you want. But let's do their closed loop. So this is a two loop, is already controller and plan together. They will just negative feedback around it. So then this is like L divided by 1 plus L. Okay, so 1 plus L, okay, is divided by both sides of case. So this is a closed loop transfer function. This is also closed loop transfer function, okay? And we do this difference. You can see the closed loop sense, their distance is quite small. The infinite norm between them are small. But in open loop sense, you haven't controlled it. This guy minus this guy, okay? You will have this will go to infinity. You can imagine the frequency domains like that. It's very, very. You can do some math in here. So it's one. So you have a in the end you have a 0.1 divided by s plus 0.1. So when s goes in 0, then it's infinity. When s is infinity, it goes to 0. So it's kind of this way, okay? This way, going down, like double integrated type. So then, of course, H infinity norm, the peak norm is infinity, because we have integrated in here, okay? However, if the closed loop system is not like this. Closed loop system, you have 1 over s divided by 1 plus 1 over s is 1 over s plus 1, okay? And here is similar, here is similar. So you have a 1 plus 1, s plus 1.1, okay? So the difference is very small, very small, okay, very small. So that means H infinity may not be nice, may not be nice. So closed loop, you are close. Open loop, you are not. Now, I hope this can be consistent, okay? More intuitively speaking, okay? So what is a gap metric, okay? Gap metric is based on a previous, we have learned, there's an example, don't worry, it's easy to do. So you can do, this is called right coprime factorization. This is called left coprime factorization. And we all assume that this is true. This is like complex conjugate, okay? Also anti-stable version of that. You replace s with minus s, okay? So that's anti-stable. This is stable, anti-stable, okay? I will see an example in the next, okay? So it's my plant. So you have a coprime factorization and you have normalized way in here, okay? And you have P is the U and Y. Okay, it's a mapping. Okay, it's a mapping. Okay, so this P is the mapping like that. So we do H2 space. H2 space multiply by this space, or multiply by this matrix, so it's a closed subspace of H2. So we are talking about, you have P1 and P2, you have two systems, P1 and P2. I want to understand the gap between them, okay? Gap between them, yes. So what is the gap? The gap between P1 and P2, for P1, you have normalized right coprime factorization. This is also true, okay? Okay. So then, what is the pi? Okay, so it's called orthogonal projection onto K. And we're going to make it clear soon regarding what is this gamma here. Okay, gamma here. And then the distance between them is called the gap metric, called delta G. G stands for gap. Delta is the difference. Okay, but I think the gap metric, okay, gap metric, they have something called directed gap. The directed gap is, that's just a notation, it's not just a vector, okay? Okay? It's not a vector. Directed gap, okay? Computed using simply putting any stable filter Q in here. And then you still use P1, this is P1, this is P2. So you have these coprime factors, and add to this one to infinity norm and choose the smallest number. So that one is called directed gap, okay? And the gap between the original P1, P2 is actually computed by choosing the larger one, okay? Larger, max between that. P1, P2, and P2, and P1, okay? Remember, this is a free parameter you can assume. You scan all of the Q. Okay. So sometimes you understand what's behind, okay? That's good. There are some iterative processing here. You need to search this Q. It's an optimization problem, okay? Again, Q is a transformation matrix of stable irrational, a substable rational, proper, okay? May not be strictly proper. So in this case, you have you can see two systems. They have distance. Open loop is small, considered as small. But remember, if you close a loop, it will no longer small. Okay. So we need a new metric that's called gap metric. Okay. So what is the gap? Lower bound. Okay, lower bound. So you have. We define a function called phi. Okay, it's a normalized phi. This is the phi is a transformation matrix constructed by like this is for P2. Okay, this is for P2. You have a left normalized coprime factors here, and here is anti-stable. Okay, it's called anti-stable. We replace S with minus S. So this is anti-stable of this is anti-stable of this, okay? And this one will be a unity matrix, okay? The anti-stable version will be unity. So with that defined, so again here, this is a directed gap, we define this. Then we add something, this phi on top, okay? You weight it. Then you choose the overall infinite norm and do optimization, find it. And then you do math, you end up with this, okay? This one. So we define this is there's a lower bound, okay? There's a lower bound by P1, P2 alone using this phi. We'll see the file defined next. So what is this phi, okay? This phi is actually nothing to do with controller, okay? It's only the original plant ones, right, right coperion factors M1, N1, and the second one's normalized, right, normalized, left, this is left, okay, left coperion factors. So that is transfer function matrix in here. So if we write in this one, and we got this relationship in here, okay? So we are going to see an example now. So giving a system, two systems, P1, P2, you can compute this immediately. Infinite norm of this one immediately. And this one will serve the bottom line of the gap metric between P1 and P2. So they are related, okay? So let me do an example here, okay? You have P1 and P2 here. So listen carefully so you will get a enhanced understanding. So original system is this. The second system is this. So you have the same denominator, but you have two different gains, okay? So we are going to do right coperion factors normalized. So Ni is I is 1, 2, it doesn't matter, Ki is 1, 2, okay? So you can see I have a rational stable system, They divided, they are going to end up with K1 divided by S plus 1. Can you see that? M is the denominator. You cancel out this one. And you have freedom to choose these numbers, okay? But I want normalized ones. Then you will see that M will satisfy what they call normalization. So I want to show you the normalization. It's called anti-stable ones. So M and is anti-stable one, N and anti-stable one add together is I. So then we are going to verify it. So can you consider to all verify that? Let's see. So in other words, N is this one, right? N is this one. But what is N tilde? Not, okay, it's different. It's complicated, sorry. I'm doing this for you, okay? So you know that N1 divided by M1 is my P1, all right? Okay? And my P1 is K1 divided by 1 plus S, okay? 1 plus S. That's what we know. But N1 is K1 divided by S plus square root of 1 plus K1 squared, okay? Then M1 is S plus 1, okay? S plus 1 divided by S plus 1 plus K1 squared. Don't you see that? So you already, basically you just try to, you have a denominator, so you divide it by something, so this is something is this one. But this one has to be chosen carefully such that N1 tilde So that's something different. So I hope you see the difference between N1 as third and N1 third as there's a difference, okay? Difference. When I say third in here, that means is equal to N1 minus S. You may say, hey, what are you doing? So I'm showing you here. So then I want to show you that plus M1 third will be 1. Let's verify that, okay? Verify that. So N1 is this guy, okay? N1 third is minus S, okay? Minus S. So then you have square. So this one will give you what? K1 squared, okay? And here is 1 plus K1 squared minus S squared, right?
Yes.
Because you replace S with minus S, so this is minus S squared. Is that right?
Yeah.
So this term is like that. The next term is the same, okay? M1 here. So I have what? I have S1 minus S squared, because I replace S, right? Is 1 minus S squared divided by 1 plus K1 squared minus S squared, right? Minus S squared. Okay. So this one will give us what? 1 plus K1 squared. 1 plus K1 squared minus S squared. So we lump that. I have K1 squared plus 1 minus S squared. So it's 1, right? So it is normalized. So this add to this one is normalized. Okay? Make sense? So N1 third plus M1 third. That's normalized. Okay? Can you see it's normalized? Yes. So there is a way why we choose this. Okay? The good news is now you don't have to. You can use computer to get all these numbers. Okay? So in this case, you use P1, P2 infinite norm is actually the gap. Okay, the gap. So we choose this one like K1 minus K2 and K1 minus K3. This one will be the way less than something like this. So this one is based on the argument previously we had for lower bound. For lower bound. Okay, for lower bound. Okay. So in other words, it's very important to study the difference between the gap between two plans, okay, and how to compute them, okay, So this gap, you can imagine what's next is to use this gap idea to understand what is the bound, okay, what is the bound for uncertainties, okay. Say for example, you have a plant P that is this P, and you have actually another P1, okay, which is the real P. The real P, you just think about the P here is the center, and P1 is anything around the center, okay? But the radius somehow is less than B. So you can see we are defining the bound using this new directional gap metric parameter. So this is a way to define my uncertainty set. The P1 has infinitely many, okay? But the distance to the nominal P is P, is B less than B. That's a new way to define the uncertainty set. And without loss of generality, we talk about B's between 0 to 1, okay? So that's not a problem. And so on the other hand, assuming that each individual P1 can be written as the normalized right factors, n plus delta n, m delta m. So while n and m is original, the normalized covariant factorization is called nominal. So these are the nominal value, okay? So this is disturbance. So this disturbance itself are H infinity norm, okay? In H infinity space, okay? So we didn't say it's irrational. It could be irrational, could be not irrational, proper, maybe not proper. We don't. So this H infinity is like that. So then this delta n, delta m together put then infinite norm is bounded by B. Okay, so these are equivalent. This is the equivalent definition. Okay, definition. So I think people invented this one first, then they come out that. Then in the end, they find out these two things are connected, okay? They are connected. But this can be rigorously proved. This gap metric and the bound on the uncertainties in the covariant factorizations are the same, This is very beautiful, actually, okay? And this gives us more confidence to look into what's this gap metric and how we can use it in our practice to guide us, using this new metric, to guide us to do a better job in loop shaping. So with, what do we mean better? Meaning we have reduced conservatism, okay? Conservatism. The proof process is not that hard, and I'm going to skip that. So let me just do this. So when this gap metric, these two are less than 1, okay, less than 1. So the distance between P1, P2 less than 1. So then these are the same, okay, directional is the same, okay. And for the P, we already said this is covariant factorization in the minimum singular values from here. And then it's already the bottom line. So this is B less than that. Okay, this is the B less than that. So if that's true, okay. So the original system is already defining this is a piece of rotten wood or not, defining the fundamental limit that you can tolerate. So basically here, B, you have pretty good idea. It cannot be greater than something. It has always less than this, giving the nominal plan. Okay? So then what you can consider is the P1, anything less than B is the same as the difference between less than B. So directional and non-directional, they are the same. And we already come out of here. This, you have seen this before in the beginning. I showed you this, and also I showed you this, BPK. And in this case, we are introducing the controller K. Okay, controller K. This is a very interesting thing to ask a question. So, say I already have a nominal system under a nominal control. Okay, nominal control. Now, I assume that my nominal system will be perturbed by from P0 to P, and the distance is less than R, the gap metric. And my controller is also got some sort of perturb from K0 to K. K0 to K, okay? So then also the distance between the controller also got perturbed. The system also got perturbed. So then after the perturbation, my real system is PK, okay? It's a PK. So can I say if they are stable or not? Okay? Okay? So this is my perturbation, all the uncertainty P with this condition, all the controller with this distance. So I pick up any P from this family, any K from this family, and then I guarantee the whole thing PK is still stable. I need to check whether this is true. There is a very beautiful result, surprisingly interesting. It's called if and only if means sufficient and necessary condition. That is the original BPK, okay? Original B naught K naught. Original this is the original BPK, okay? And arc cosine of this guy will be greater than this 2x. Isn't this surprising? I feel this is very surprising. And also very beautiful. They can be proven very beautifully, okay? In this case, we're talking about worst possible performance resulting from the sets of plans and the controllers given by this, okay? So what is the minimum, infimum, okay? Infimum means the smallest possible one, okay? Is actually given by this difference, okay? Okay. So that actually is shown in our book. If you are interested, I'm going to upload a book by YangQuan, okay? So he wrote a dedicated gap-metric book for robust control. And all these results, they have very detailed derivation for you. And I think it's a good idea we look into an example, okay? Then we finish from here, okay? So I have P1 and P2. So you can see the only difference is my numerator is different, but it's very interesting. You can see I want this one to have a normalized coprime factors, and so N1 is this, M1 is this. So, okay. So what do you do? So then this N tilde plus M tilde should be 1. So then this side is 1/2, this side is 1/2, this is 1 minus a square, and here is 1 minus a square, okay? Okay, so this half plus half is 1. Makes sense, right? So minus s, times this is 1 minus s squared, okay? This is 1 minus s squared, okay? So you did that, will be half, okay? Only half. N1 tilde is half. M1 tilde is half. So half is 1. So it's normalized. Same thing is true here, okay? Same thing is true here. You may wonder how I can do this, you know. And that takes long. There's something called Bezu identity. Bezu identity. So giving polynomials, how to automatically find out what is the magic numbers in here, how to do that. There is a called polynomial toolbox. Right now, polyx, okay? MATLAB toolbox, POLYX, polyx. But I don't think they are still selling it. So I was a former user of this toolbox. They can give you a symbolic or everything here, okay?
So is that unique or not unique?
If it is normalized, it's unique. If it is not normalized, it can be anything, okay? So you can imagine, okay? You can imagine. So what if you put, say, you bracket, put here s plus 10, you also do s plus 10, they all cancel out, right? They all cancel out. But you add that one, you will not normalize to 1, okay? You will not. So the difference between P1 and P2 is 1/3. And inside here, the H infinity norm between this phi P1, P2 will be like this. So you can see the gap here, they will give you 1/3, okay? And so what this one is trying to argue here is this one says that the P1 here, okay, B optimal for that is 1 over square root of 2. The optimal controller achieving this one is 0. Okay, that's something wrong with this. You agree? So in other words, you have to have some sort of uncertainties there. So the P is to find out by using this. So the P family is the distance less than B optimal. This is 1 over square root of T. That's square root 2. So the P is in here. And because of the uncertainties in here, so we can say, oh, P is n plus something like here. So in our case, we can set this one 0, this one to be another one. So then, after the derivation, you are going to see you have coprime factors uncertainties given. Okay. So next is an example we are going to go through next time. It's very simple though. It's unstable, open unstable, but you have interval uncertainties in here. So I want to understand: is it true that what is the nominal plan for that? So usually you say, oh, go in between half, then put it here as a nominal plan. Can we just say that? So what is the best nominal design model for P0? Or is this in between here, like half of it? The answer is maybe surprising, is no. That depends, what do you mean, okay, nominal. So really we use gap metric about distance. Then we decide the suprema of this one and the infimum of the K, okay? So you got a nominal model here, okay? Scanning gap metric. Then you choose what is the K0 in here. This is a nominal model. Then you do infimum. Okay. So we are going to go through this example next time. Just let you know, doing average is not the good way to do the nominal system. So if you have a wrong, not very good nominal system, you design everything around that, may not be good. May not be good. The gap metric answers question about how to decide the best nominal model given that set. Okay? So it is not in the middle, okay? It's not in the middle. So we are going to go through this example next time and how we can go from it. I know it's a little bit hard to understand all this, but I already said using some simple idea about distance, okay? Distance is a gap, okay? It's a gap between this and this. So we use this gap to decide the uncertainty. Okay, beside answer as a distance measure. So we'll continue the gap metric. I think it's a very interesting topic. So, I think a lot of schools they do not go this far on gap metric, but I believe it's useful for you. In the future, whenever possible, check the gap. Okay, mind the gap. Okay, so thank you. And we are going to meet Wednesday. I'm going to be in my new office, 327. So you are welcome to visit me.